So we're finishing 3-2 today, doing 3-3, and then hopefully starting 3-4. I've not assigned any homework, so you guys had no homework to do, which is hopefully good. Hopefully you were able to enjoy your Thanksgiving break. It was nice, thank you. We got to do these first two problems on this side, and that will finish 3-2 for us, just some word problems. And then we'll do 3-3. We have all the rest of that page finished, right? Did we do all the way up to number 8? Can someone confirm or deny for me? Yes. Okay, perfect. So we're on number 9. Awesome. So I know you probably spent your whole Thanksgiving break thinking about pre-cal, but in case you didn't, let's review kind of what we're doing. We're in our exponential unit. And so at the beginning of 3.2, I'm just flipping to the first part of the 3.2 notes. I taught you these two formulas. So we were using y equals a times b raised to the x before in like 3.1. That's just a basic exponential function. When we started 3.2 though, I told you this formula, p of t equals p sub 0 times 1 plus or minus r raised to the t. This is the exact same thing as the exponential one. I think I talked through this with you. The p of 0 and the a are your initial values. The b is what we're raising our exponent to, and that's the same thing as 1 plus or minus your rate. And then your x and your t are both those like variables that we're plugging in and solving for. So we're going to use the p of t formula down on the next part on 9 and 10 to write our formula. So I just wanted to show you that we've looked at those, but I'm sure you probably don't remember it. So I'm just going to rewrite it up here at the top. So p of t equals p sub 0 times 1 plus or minus r raised to the t. I'm going to give you all those parts so we can write an equation. And then from that equation, we're either going to plug in for t and solve, or we're going to plug in for p of t and then go to our calculator and graph and see where they connect. So the first problem says the 2000 population of Jacksonville, Florida was 736,000, and it was increasing at the rate of 1.49% each year. At that rate, when will the population be 1 million? Okay, where do I start? Where do I plug in first?
T, isn't T equal 0?
We could plug t in for 0 and figure out what my starting point is, but I actually know what my starting point is, and I know my rate. So we're just going to plug in those 2 points, and then we'll have t stays as my variable. So what is my initial starting point? Where did I start? Good. So in the year 2000, we started with 736,000. So that's going to go for my p sub 0. So I'm going to write p sub t just to like keep my best math practice going. And it says it was increasing at a rate of 1.49. Am I going to do 1 plus the number or 1 minus that number? Plus. And then how do I make 1.49% into a decimal? Move it over 2 spots, 0.0149. Very good. And we'll keep that raised to the t. If we need to plug something in, we will. If not, we'll keep it there. The only other thing I want to do before we finish this problem is I want to just combine the terms inside of that parentheses. I'm just going to add them together. So I've got p of t equals 736,000, 1.0149 raised to the t. Some of you might have already done that. You might have just physically added them in your head instead of putting the plus sign. That's fine. I just want to make sure mine's nice and pretty too. Okay, the actual point of this problem says at that rate, when will the population be 1 million? What do I do with 1 million? Where does that go? My p of t, very good. So that goes in for like my y value. It goes into the left-hand side. And so I'm going to put 1 million over here. Now, we're not at a place to solve that by hand. Let's go put it in the calculator. We've done that a couple of times, and let's just kind of get that moving in our brain again. I'm going to make our equation be our y1 and our 1 million be our y2, and we're going to graph and find the intercept. I'll zoom out in a second. Find intersect. Make sure you have your x is being raised to the exponent. Make sure it's higher up than everything else. Make sure you have the right number of zeros. That's usually a common mistake we make because we don't have the right number of zeros. Now, before I press graph, I'm gonna have to go play with my window because I just made my y2 be 1 million. So my y max needs to be bigger than 1 million. Right now mine's at 5. So if I just press a graph, I'd be really stressed out because it didn't like show me what it needed to show me. I wouldn't see what I needed to see. So I'm gonna go over to my window and I'm gonna make my y max, I'm gonna make it 1 million, what is that, 500,000? That might be a little bigger than it needs to be, but I wanna make sure that I really see the point of intersection. 2 million might be too big, but like a little bit over 1 million, I think is gonna be good to help me see what I need to see. For my X max, I don't really have a good guess. My only guess is that it said in the year 2000, the population started at that. So it can't be too much bigger from where we are. So like 150 might be a little much. Maybe I'll just do 50 and kind of see where we are there. Again, I'm just kind of guessing on that X. I want to get the best window possible before I go graph, but if I need to adjust, I can adjust. Anybody questions on my window? Okay, let's go press graph. Oh, nice. I see a really clear intersection point. I'm going to do my second trace, find my intersect, and I will do my prompts say left bound, right bound. Yours might say first curve, second curve. Just follow your prompts. Anybody have a problem with their graph?
How do you raise the T?
See underneath the clear how there's like a little upside down arrow mark? That's called a caret, and that shows it goes up to an exponent. You get it, Blair?
Yeah.
Perfect. All right, so I found the point of intersection was at 20.7, comma 1 million. Well, obviously the y was going to be 1 million. That's what we said for y2. So the x is what matters to me, that 20.7. So we're going to round that up to 21 years. So after 21 years, Jacksonville population should be 1 million. And what's kind of fun and relevant about that is we are in the year 2021, so that's 21 years after 2000. So technically this year it should be at 1 million. Last class we Googled it, it's a little bit over 1 million of a population in Jacksonville. But kind of cool that it's modeled this way. But as we know, real life doesn't always move according to a model, so it's kind of fun. These are like not very fun this way, but that's okay. Let me have my thing, right? You guys ready for the next one? All right, similar idea, but this one's talking about a half-life. I feel like half-life always like stresses us out. When we're doing a half-life, are we increasing or decreasing? Decreasing by how much? Half, so 50%. So when you see half-life, you can think, okay, we're going down, we're decreasing, our rate is decreasing by 50%. The half-life of a certain radioactive substance is 65 days. So every 65 days, we lose half of what we had. And there are 3.5 grams present initially. So letter A says express the amount of substance remaining as a function of t time. That just means write an equation. So we're going to write an equation. We're going to use our P of T formula like we did before. What's my initial amount? How much did we start with? 3.5 grams, good. And you told me that it's decreasing by 50%. So you can think of that as 1 minus 0.50, or you can just think, oh, it's a half-life. So what's in the parentheses is just 1/2 or 0.5. Now, it doesn't have a half-life of every day. So like every time we do it, it's not going to lose half of it. It happens every 65 days. So to represent that, we're going to have our exponent of t divided by 65. After like 40 days, it's still lost something. It just hasn't lost a full half yet. So we have to like take that into consideration. It doesn't lose a full half until 65 days, but every day that happens in that 65 days, we lose a little bit. So we represent that by t divided by 65. Okay. Letter B says, when will there be less than 1 gram remaining? Where does the 1 go? Good, P of t. It says, when will there be less than? What inequality sign am I going to put in between those? When will the quantity that I have be less than 1 gram? A what? I want to put a greater than sign because everything that's on the right-hand side must be smaller than the 1 gram. The reason it's not a less than is because the way this formula is set up is the y is always on the left side instead of on the right side. So if you want to do a less than, that's fine, but it has to then be moved over here to be like this instead. Either way is fine. And truly, it doesn't matter. We're going to get enough information when we plug in and find our t, because it'll just be after that many days, it should be smaller than 1 gram. So we're going to go plug my equation in for my y1. I'm going to go plug 1 in for my y2, and we're going to graph. And we're going to have to play with the window again because I just had my y max at like over 1 million. And now it's like 1 or less than 10. So we're going to have to think about that in a second. I also want to caution you that you may need parentheses around your x divided by 65 in order to show that it's all in the exponent. So when I show my graph in a second, if you don't get what I graphed, you might need to put parentheses around your x divided by 65 to show that it's all in the exponent. My window, my y max has to be way smaller than that. I'm going to make my y max just 5. Technically, it can be as small as 3.5 because that's how much I started with, and it's just going down from there. But I like to see enough of the picture, so I'm going to do 5. And then my x max, do you think I need more than 1 whole half-life to get to less than 1? What would it be half of 3.5? 1 point something though, right? So we're going to need a little bit more than a half-life, right? So we need to make sure that our x max is bigger than 65. What should we guess? Anyone have an idea? It really doesn't matter, right? It could be 100, it could be 150, it could be 300. We don't know. We just are going to make it a little bit bigger. So I'll just try 100 and see where we're at. All right. My graph looks like I still need a little bit more, so I'm going to change that that x max, to 150. And again, that was a little bit of just trial and error. I knew it had to be more than 65. I just didn't know how much more, but I definitely see it now. If you have a problem with your graph, remember, go change your exponent, make it sure it's got parentheses around it. Anyone have any questions about their graph? Second trace, find that intersection, left bound, right bound. My point of intersection is at 117. So I'm going to say t is greater than 117.5. And we like to round up. I don't want to do 0.5 of a day. We'll say after 118 days, we will have less than 1 gram of my substance left. All right, that's all for 3-2. So as of right now, your 3 homework will be due next time I see you. Anybody have any questions yet? Okay, we're gonna jump into 3-3. And I actually like 3-3. It's a lot of basics of logs. There's no word problems in this section, so that's kind of fun. So those were the only 2 word problems we're doing all day. How exciting. Just got it out of the way. Moving on. And I actually don't need my calculator anymore. Okay, what we have going on here is you see all of these log problems. Log and exponential functions are inverse functions, so they go together. It's like square roots and squares. It's like adding and subtracting. Logs and exponentials are inverses of each other. What I'm going to teach you, and every teacher does this a little differently, but I think it was an Algebra 2 teacher, she taught us something called a log roll. And that helps us move from log form to exponential form. So let's say we've got a log in the form of log base A of B equals X. What are you laughing about, MK? Oh, a loop-de-loop? Okay. Did Miss Lettington or Miss Hollis have some cute name for it? Oh, nobody learned it? Okay, great. You're about to learn something so exciting then. I think a log roll is nicer than a loop-de-loop, but you can call it a loop-de-loop if you want. Okay, what happens here is we're going to start with the base. So the base is the small number under the log. So I'm going to start there, and I'm going to roll underneath the equal sign and then back through the B. Okay. What cute name did they have for it? No cute name? Okay, well, you're going to remember a log roll. That'll be the cute name you remember. And the reason I like drawing it like this is, do you see how it looks like a little cursive E? I started at the base, and then I went through the X and then back through the B. It makes a little E because I'm now going into exponential form. So the first letter I touched was A, so that's what I write first. That's the base. The next letter I touched, or the next number I touched, was my X. That becomes my I lost you guys. Are you back?
Yeah, we're good.
Okay, good. All right, I'll look at what I just talked about in case you missed it. So that's what we're going to do for all of these. So again, our log roll, we started with the A, we started with the number underneath, we looped around to the X and then back through the B. We rolled all the way around. So A to the X equals B. Same thing as what we just did on that first one. So I had 5 was my base, wrapped underneath for my X and rolled through to my 5. 5 to the X equals 5, and you guys easily told me that should be 1. 5 to the first is my answer. So let me pin my video. I don't know if that changes on the recording. There we go. 5 to the first equals 5. Let's do the same thing on the next one. This is all about repetition. Okay, I'm going to set it equal to X again, and I'm going to start at my base, and I'm going to roll around. 4 to the X equals 16. Well, 4 to what power equals 16? 2. Very good. Okay. I always give you 2 super easy ones, and then you're like, I know the world's going to implode next. It's not going to implode, but there's some special cases I kind of want to work through with you. What does this ln mean? Natural log. So ln means natural log. And do you know what my base is supposed to be there? ln is the same thing as log base what? E. Log base E. E is like a number like pi. It's a special number that we like kind of only look at in exponential and logarithmic days. But I can rewrite this ln to be log base E. And then I still have to write what I'm doing the log of, which is e to the 10th. I like to rewrite it this way so that I can do my log roll super easily. I can do e to the x equals e to the 10th. Whatever is in this spot that we're doing the log of carries with me. And that's why it's at the end, because it goes through all the way to the end. E raised to the x equals e to the 10th. And while you might have been stressed out about the e's, if my base is the same, then that means my exponents also are equal. So that's x to the 10th. Sorry, x equals 10. I don't know why I said that funny. X equals 10. Okay. What about the next one? I've got an ln, so I'm going to make that log base e. Oh, sorry, 10. I'm moving too fast. I've got this cube root of e. Do you remember how to make a cube root or a radical back into a exponent? Cube root of e is the same thing as e to the what power? You remember? not the third. Close. The what? 1/3. Very good. The 1/3. So the fraction is what makes it a radical. Fraction is what makes it a radical. So I've got log base e of e to the 1/3 equals x, and then I can log roll that around. E to the x equals e to the 1/3, so x equals 1/3. A lot of things I teach you, I have a reason behind it. I don't really have a good reason for this next one. I'm sure there is one, I just don't really know it as well as everything else. This one says 6 raised to the log base 6 of 10. Because the number that is being raised to the exponent is the same as the base of the log, that all cancels out, and I'm just left with whatever that last number is, 10. So this all is just equal to 10. Similarly, for the next one, I've got 8 raised to the log base 8 of 2. They both have 8 as the base of my exponent and as the base of my log. So those all cancel, and I'm just left with 2.
Does that also cancel out the log?
Yes, the logs cancel too. The 8s and the logs all cancel. Okay. Do you remember what happens when I've got a number out in front of my log? Do you remember where that came from?
Distributing.
I don't want to use the word distributing. It comes from the exponent. So when you have an exponent of a number inside of a log, it goes, the exponent goes with that base, and you could put it out front. We're gonna deal more with that next class. My other classes, they either like definitely remembered or like one class had no idea either. So I don't expect you to know that. That's why we'll go over it. But that 4 is like the exponent. So I can move that 4 to the exponent and say this equals x and still do my log roll. So I'm gonna do 2 raised to the x equals 2 raised to the 4th. And that makes x equal 4. Let's do number H and then we can go to lunch, okay? Number H says e raised to the ln of 6. This is a lot like letters E and F, where it was like 6 raised to log base 6, 8 raised to log base 8. E raised to ln is the same thing as e raised to log base e. So that cancels out, and I'm just left with 6. Okay. We're gonna do like 3, 4 more when we come back from lunch, and then I'm gonna have you try some more, and then we've got a few more problems left. Cool. Let's come back at 12:20. That seem fair? Awesome. Have a great lunch. And you guys, I'm just gonna mute myself, but if you're welcome to leave and then come back. So 12:20, we're gonna start up again, okay?
Yeah, Miss White, I got a few things.